Lesson 2, that's a spicy pizza. And this is about the area of circles. So we did the circumference in the first section, then we're working on the area of circles in the second section. If I take a look at the learning goals, first, give an informal derivation of the relationship between the circumference and area of a circle, and use the area formula to solve problems. Fancy language. Tell the difference between the circumference and the area, and then be able to solve problems depending on its circumference or an area problem. Decide whether circumference or area is an appropriate measure for a problem situation. Calculate unit rates associated with circle ideas. Key term is unit rate. You have learned about the different parts and measures of a circle. That is true, including radius, diameter, and circumference. How can you use the parts of a circle to determine the area of a circle? Okay. In the warm-up, determine a unit rate for each situation. So a unit rate, if I'm looking at these are rates, which is a special kind of ratio that is comparing two different units. For a unit rate, all that they're saying is I want to see what it would be to have one of something. And so for all of these, I want to see what it would be to have one of something. To get one of something. Okay? And now, when I look at these problems, to get from 16 gallons to 1 gallon, I would have to divide that part of the ratio by 16. Whatever I do to one part of the ratio, I divide the other part of the ratio by the same thing. So we have 38.40. Divide that by 16, and then I get 2.4, and it's money, so I have to have the pennies place, and I should have a dollar sign. The next one, to get from 3 7/75 hours to 1 hour, I have to divide this one, sorry about that, I have to divide this by 3.75. I would do the same thing to the top to see how many miles I would jog in 1 hour. So divide that by 3.75. 3.75, that's getting close to a marathon for me, give or take. Then for this one, we would have 15 divided by 3.75, and that would be 4 miles in 1 hour. Okay, so that's like that's like a 15-minute mile. All right, then. Then the last one, to get from 15 pounds to 1 pound, I have to divide that by 15. I would have to divide the top of this ratio by the same factor, so I'm scaling it down by a factor of 15. 26.99 divided by 15 equals $1.80. I would round it to the nearest penny here, and so I would do that. All right, so that is the warm-up, and this is sections about ratio. This section is all about the area of circles, and we will be also working on our ratios and rates as we get going here. All right, so getting started, what changed, what stayed the same? The length of the base and height are the same in the parallelogram and rectangle shown. How could you rearrange the parallelogram to create the rectangle? So if I have my original parallelogram, which is kind of like that, give or take. That is not a good drawing, I apologize. I would cut off the triangle part of the parallelogram. Then I would move that triangle part from right there, and I would put it right next to it right there. Oh, there we go. And so I would cut the parallelogram perpendicularly at a 90-degree angle and rearrange the pieces to make a rectangle. Okay. What is the area of each figure? This is confusing, but they're kind of saying if we have a parallelogram, any parallelogram, the area would be equal to the base times the height. Just like if we had any rectangle, the area would be equal to the base times the height. Because we don't know exactly what B stands for, we don't know exactly what H stands for, so we're using the variables to represent the formula. And the parallelogram formula is the same as the rectangle formula because we can rearrange a parallelogram into a rectangle. Okay. All right, so activity 2.1, deriving the area formula. In the last lesson, you derived formulas for the distance around a circle. In this lesson, you will investigate the space within a circle. Use the circle at the end of the lesson that is divided into 4, 8, and 16 equal parts. Number 1, follow the steps to decompose the circle and compose it into a new figure. A, first cut the circle into fourths and arrange the parts side by side so that they form a shape that looks like a parallelogram. B, then cut the circle into eighths and then sixteenths. Each time arrange the parts to form a parallelogram. All right, so that should have been done. There was nothing really for you to write in after you did it. I do want to show you what it looks like. And so if I was to take this out, this one, you can see that when we first cut it into fourths and arranged it going back and forth, it kind of looks like a parallelogram. Then we cut it into smaller pieces, and I believe these are eighths, and then you can see that it got closer to looking like a parallelogram. And then sixteenths, it got even closer to looking like a parallelogram. And so hopefully yours looks something like this when you did that. Next, analyze the parallelogram you made each time. How did the parallelogram change as you arranged it with the smaller equal parts of the same circle? It looked more and more like a rectangle. What would be the result if you built the parallelogram out of 40 equal circle sections? What about 100 equal circle sections? It would continue to get closer to being a rectangle. C, represent the approximate base length and height of the parallelogram in terms of the radius and circumference of the circle. This was a tricky one, but this is the one I've kind of been drawing here a lot for warm-ups and stuff. It was kind of a big jump, it felt like, when I was doing it myself. Okay, so when I was to take this, I know that this height is from the center to the outside, so that's going to be the radius. Then I know that this base, well, this is half of the circumference and this is the other half of the circumference because we have the pieces going every other way, kind of switching off. And so if circumference is diameter times pi, then half of that we could say would be radius times pi. Okay? And so represent the approximate base length and height of the parallelogram in terms of the radius and circumference of the circle. The height is the radius of the circle. The base is half of the circumference which is radius times pi. Use your answers in part C to determine the formula for the area of the parallelogram. Okay, so I kind of did that on the last question. That happens sometimes where they're asking for a little bit and not as much. I know that the area of a parallelogram would be the base times the height of those circle sections that are put together. I also know that the height was the radius, and I know that the base was half of the circumference. I could rewrite that, and I'll do so down here for this question. How did the area of the parallelogram that we made compare to the circle? Well, the whole circle was cut up and put into that parallelogram, so the areas are the same. Write a formula for the area of a circle. Well, the area is going to be the radius, and then half of the circumference is going to be the radius times pi. And so if I already have a radius, a second radius, I could rewrite it as r squared times pi. Use the different representations for pi to calculate the area of a circle. Calculate the area of each circle with a given radius. Round your answers to the nearest 10,000ths if necessary. All right, so if we're using pi, and I misled people here, r squared would be 36 pi. 1.5 squared is 2.25 times pi. And then 1/2 times 1/2 is 1/4 times pi. We probably could write that as 0.25 times pi as well. Now let's try using this. Let's see here, 36 pi key on this calculator just says it's still 36 pi. I have an idea about why. Now this is 2.25 pi, and this one gives it to me here. So 7.068 and then 58, and so it would round up to a 6. All right. This was a decimal. This was a whole number. And so I think that's what's determining if the pi key gives you an answer, if it doesn't give you an answer with this particular calculator. Then we have 0.25 pi, and that gives us tenths, hundredths, thousandths. 10 thousandths is a 3. The next digit over is a 9, so it would round up to a 4. Okay. Next, I use 3.14, so the first one is 36. 36 times 3.14, and that is 113 and 4 hundredths. The next one is 2.25 times 3.14, and that's 7.065. This one's a little lower than the pi key. Okay, and then the next one is 0.25 times 3 and 14 hundredths, and that is or 0 and 785 thousandths. And that one's a little bit lower than when I use the pi key. Okay. If I use the fraction, I would take, let's see here, I'll write it out over here. Write it out over here a little bit. Okay. 22 over 7 times 36 over 1 is equal to 792 over 7. And I get 113 and hundredths, thousandths, 10 thousandths. So this one is a little higher than this one. Okay. Then I do the same thing here. I would do, let's see here, 22 over 7 times 2.25 over 1 gives me 49.5 over 7, which is 7.0714. Rounded to the nearest 10,000th. Oofta. So this is a little bigger than this one, okay? Next, I would take 22 over 7 times 0.25 over 1, which is 5.5 over 7. And that gives me 0.7857. So this one's a little bigger than this. So compare your area calculations for each circle. How did the different values of pi affect your calculations? Well, when I use 3.14, my area is lower by a little bit. When I use 22 and 22 sevenths, my area is greater by a little bit. When I use the pi key on my calculator, it only works for decimals. Yours might have been different. And that number is a little bit higher than, it's a little higher. This key is it's in between this one and this one. This answer is in between the two of them. Okay. So this one was in between, at least on the two that we got answers for. Okay. So that is that. All right. So this is a tricky one because we haven't dealt with a lot of ratios yet. Suppose the ratio of radius lengths of two circles is 1 unit to 2 units. What is the ratio of areas of the circles? Experiment with various radius, I should say radii, lengths to make a conclusion. So 1 to 2. And so then I first made it so I would have a radius of 1 and then a radius of 2, because that is a 1 to 2 ratio. When I calculated the area, this is 3 and 14 hundredths units squared. This is 12 and 56 hundredths units squared. When I took 12.56 and divided it by 3.14, I got 4, which means that this area was 4 times larger than this area. The radius is 2 times larger than this radius. The area is 4 times larger than this radius. I did it with a couple of other examples. Then I selected a radius of 2 units and a radius of 4 units. And when I got my areas, if I took my larger area from the 4 unit radius and divided it by the smaller area with the half as large radius, I got 4. So this radius is double the size of this one, and the area is 4 times the size of this one. Or if I said it the other way, the radius of 2 is half as big as the other radius, but the area is a quarter the size of the other radius. One more example. I took a radius of 3 and then a radius that would be double that, a 1:2 ratio. And when I took the areas and I took the larger area and I divided it by the smaller area, I got 4. So this radius is double the size of this radius, but the area is 4 times the size of this radius. Okay, so if the radius length is doubled, the area is quadrupled. I spelled that wrong. I apologize. And I've kind of mentioned in passing, it has to do with the fact that in the formula, we square the radius. But I digress on that for right now. That is the pattern you should be seeing there. Activity 2.2, circumference or area. And this is something we have worked a lot on, I would say. Circumference of a circle is the distance around the circle. So it's the perimeter. While the area of a circle is the amount of space contained inside the circle. When solving problems involving circles, it is important to think about what you are trying to determine. 1. A city park has a large circular garden with a path around it. The diameter of the garden is 60 feet. Gina likes to walk along the circular path during her lunch breaks. How far does Gina walk if she completes one rotation around the path? And so she's not covering everything inside of it, she's going around, so that's perimeter. And so perimeter for circles is going to be circumference being equal to diameter times pi, or pi times diameter. The commutative property of multiplication says I can flip those two around. We're given the diameter of 60 feet, so the circumference is going to be equal to 60 times 3.14. And I'm a broken record, but as you are showing these, you should be showing your work for what you are typing in to get these answers. Down the formulas each time because of our brain. And this would be 188 and 4/10 feet that Gina would be walking. Okay. Jason works for the city park department. So it's the same situation because it's 1A and then 1B. So it's still with the city garden that has a diameter of 60 feet. Jason works for the city park department. He needs to spread plant food all over the garden. All over the garden. What is the area? Oh my gosh. They tell you what is the area, what you need to find of the park he will cover with plant food. Again, area, and I can look up here for the time being, but I should be knowing this, would be considered r squared times pi. You could also write pi times r squared because the commutative property of multiplication, I can flip the numbers around, I still get the same answer. For this one, I have to make sure I don't get messed up. If the diameter is 60 feet, then the radius is going to be half of that. It's going to be 30 feet, and so it's going to be 30 squared times 3.14 for the area. That is going to be 900 times 3 and 1400ths. Type it in here. 900 times 3 and 1400ths. And I get 2,826 feet squared is how much land he needs to cover with the plant food. Okay, so all right, so we have Samantha, and she's making a vegetable pizza. First, she presses the dough so that it fills a circular pan with a 16-inch diameter and covers it with sauce. What is the area of the pizza? And so they're talking about taking this and they're talking about filling it. Okay? And so they're saying that the pizza has a 16-inch diameter. And so they're asking for what the area of the pizza Samantha will cover with sauce. Okay? So this is an area problem. R squared times pi. I know the diameter is 16 inches. So because of that, I know the radius should be 8 inches. And so area is equal to 8 squared times 3.14. And that would be 64 times 3 and 1400ths. Then if I'm typing that in, 64 times 3.14, and I get an area of 296 hundredths inches squared. Okay. Number 3. Members of a community. Members of a community center have decided to paint a large circular mural in the middle of the parking lot. The radius of the mural is to be 11 yards. Before they begin painting the mural, they use rope to form the outline. So it's the outline, so they go around with rope, going around like this. How much rope will they need? So this is a question where they're asking for the circumference. And the circumference is diameter times pi. And so if the radius is 11 yards, the diameter would be 22 yards. And so circumference is 22 times 3 and 1400ths. And the circumference would be 22 times 3.14, which is going to be 69 and 800ths yards. And it's circumference, so it is one-dimensional. It's a line. All right, and so that is that problem. All right, so now we are dealing with activity 2.3. In activity 2.3, unit rates and circle area. Okay. Tallarico's Pizza has a large variety of pizza sizes. So we have small, medium, large, extra large, and then like enormous, ginormous, colossal, but they spelled it weird. Diameter of the pizza, so 10, 13, 16, 18, 24, 28, and 36 inches. So it's obviously getting larger. The amount of slices in that pizza when they cut it up, but that wouldn't change the area or the perimeter of the pizza. And then the cost, how much you would have to pay for each of those different sizes of pizza. Okay. Lena and Michael are trying to decide whether to get 2 pizzas or one ginormous pizza. They ask themselves which choice is the better buy. Okay, so basically, better buy is cheapest. All right, so they want to go with cheapest. All right. They each calculated a unit rate for the ginormous pizza or ginormous pizza. Notice the little hints thing here. You want to pay attention to those. Recall that a unit rate is the ratio of two different measures in which either the numerator or denominator is 1. Okay. 1, and that doesn't look like a 1, it looks like an I. So Lena has the thumbs up. That means what she did is correct. Okay. 1 ginorme pizza. Notice what she has here. I looked at the ginorme up here, and it's 28 inches, and so the radius would be 14, so it's 14 squared times pi. And then on the bottom is the price. And so what she was trying to do here, and I'm a little concerned because not many of you were asking me about this, and you should have, because it didn't make sense. Okay. So first, she took the 14 square. She got 196 times pi divided by 28.99, and that is about 21.24 square inches per. All right. If I took 196 and I divided it by 28.99, I don't get that same thing, because here's the thing that they didn't show for Lena or for Michael. All right. So I needed to take 196 times the 3.14 to get the whole thing. When I do that, I get divided by, there we go. I get 615.44, and that's square inches of pizza. And then I would divide it by the price. And when I divided that by the price, then that's where I get about, and that's a little squiggly line right there because it's about, it's not exact. But they got 21.2, and I got 21.23 square inches of pizza, or inches squared of pizza per dollar. So per $1. All right. And so if I was to think about this from our warm up in this section and in the first section, I would almost be thinking of this many total square inches on the pizza to this many dollars. And I want to scale that down for how much $1 is worth. To do that, I divide this part by 28.99. I do the same thing to the top of the ratio, 28.99, and that's where we get the 21.23 inches squared per dollar that I have to spend. Okay? And so if I think about it, the more inches of pizza I get per dollar, that's the better buy. Okay? And so even though there's no questions on this page, I have to look this over really carefully. I have to study this carefully so that I can understand the problem. On the example, I need to go over these. Whenever they give these gray boxes like this and there's a thumbs up, that's someone that did the stuff right, but I need to go over it carefully and make sure I understand that. I only got a couple of questions from you guys about this particular problem. So, buttons. All right, so first I want to look over Michael's work. And so 1 ginorme pizza, it was $28.99 for that size of pizza. Once again, figured out 14 squared, had it as 196 times pi, and that's about 5 cents per square inch. Again, the thing they left out of this is I would take the 196 times an approximation for pi to get it, so it was $28.99 for 615 and 44 inches squared for that much pizza. And what they're doing is I want to know how much it is, how much I pay for 1 inch squared of pizza. And to do that, I scale this down 615 and 44 hundredths. I divide that. So that divided by 615 and 44 hundredths will give me 1 inch. And then I do the same thing to the top part to scale down the ratio. And that is equal to, let's see here, 28.99 divided by 615.44, and that I get equal to about 0.047 rounded to the nearest penny would be about, that's the curly, I'm sorry, that's not very good, but the curly wavy line right there, it's about 5 cents per square inch. Okay, the ginorme costs approximately 5 cents for each square inch of pizza. All right, and notice what Lena did here. Lena has it where it's this many square inches per dollar. All right, so both of them have thumbs up. So both of them are correct. Consider Lena's and Michael's work. Explain why Lena's and Michael's unit rates are different, but still both correct. Well, Lena calculated how much pizza per square inch, while Michael flipped it around, and Michael figured out how much money I said that wrong. I need to redo this, don't I? Wah, wah, wah. Cross out my work. It doesn't have to be fancy. This is my work as I go. All right. Lena figured out how much pizza per dollar spent. And then Michael figured out how much money per 1 square inch of pizza. Okay. So we're all going to make mistakes. When you make mistakes, you want to go back over your work and make sure you have the right thing going on right there. How would you decide which pizza was the better buy if you calculated the unit rate for each pizza using Lena's method versus Michael's method? All right. So for Lena's method, for Lena, I would know it was a better buy the more pizza I got for $1. For Michael, I know it would be the better buy the cheaper it was per square inch of pizza. So for Lena, the bigger top number would be a better buy because it'd be more pizza for a certain amount of money. For Michael's, the smaller top number would be the better buy because it's cheaper per the same amount of pizza. So they're kind of flipped around, but they both get you the right answer. I'm going to pause this and I'm going to start this again. All right, number 2. Which of the 7 sizes of pizza from Tallarico's Pizza is the best buy? Explain your answer. All right. So the top one in black is what I did for Lena. So I took the area of the pizza, I divided it by the price to get $11. I'm sorry, 11 and 23 hundredths inches per dollar of money spent. Okay. Again, with Lena, the more pizza I get per dollar, the better buy. And so if I go across here, that many inches of pizza per dollar, this many square inches of pizza per dollar, this many square inches of pizza per dollar, this many inches of pizza per dollar, this many inches of pizza per dollar, this many inches of pizza per dollar. So for Lena's method, the ginorme is the most amount. Okay. For Michael, I have the price on top. So the price divided by the area of the pizza, r squared times pi. And so 9 cents per square inch, 8 cents per square inch of pizza, 6 cents per square inch of pizza, 6 cents per square inch of pizza. And here's where it becomes tricky. It's 5 cents, 5 cents, and 5 cents. But what I can tell you is this was over 5 cents and it rounded down to 5 cents. This was over 5 cents and it rounded down to 5 cents. And this was under 5 cents and it rounded up to 5 cents. And so this one was also the best buy, but when we round to the nearest penny, you cannot see that. Okay. And so what I would say here is the ginorme is the best buy. I calculated it by finding the unit rate, how much pizza I would get per dollar, and it was the most pizza per dollar. And I calculated it with Michael's unit rate of how much money per square inch, and it was also the cheapest of how much money per square inch. And so that is how I answered this question. I calculated all the unit rates, and I found the one that gave me the most pizza for the least amount of money, and I found the least amount of money per square inch. All right, now we have the talk, go with the flow. That last problem related back to our warm up from lesson 1 and from lesson 2. As I'm going through this thing called math, I want to keep on thinking, where does this relate back to? Like, is this problem like something else I've already done? Which pipe configuration can deliver more water to residents? 1 8-centimeter pipe or 2 4-centimeter pipes? Show your work and explain your reasoning. This reminds me of the ratio problem of a 1 to 2 ratio when we're talking about the radius of the different circles. Okay. This whole section was about area, so I do know that we're looking at area, and I'm also thinking about how much water can go through the whole pipe, and that would be covering the whole pipe, and that would be area, that would not be perimeter or circumference. Okay, so if that's the case, I'm going to start by calculating the area of all of these circles. So for this, area is r squared times pi. I always write the formula first. I want to show my work. If I show my work every single time, guess what? The formula is kind of stuck in my head because I've been doing it for every single problem. Then I have 8 squared times 3.14, which is going to be 64 times 3.14, which I will use my calculator for. And I get an area of 296 centimeters squared for the 8-inch pipe. Okay. Then for the 4-inch pipe, same thing, and they'll both be the same. So it's going to be r squared times pi. That's going to be 4 squared times 3.14. Then that is going to be 16 times 3.14. And my calculator will tell me that it's 16 times 3.14. And I get an area of 50.24. All right. And so now, and that would be centimeters squared. Same unit. So this is 200.96 centimeters squared. This is 50.24 centimeters squared. This is 50.24 centimeters squared. Okay. If I was to add these two together, 50 and 24 hundredths and 50 and 24 hundredths centimeters squared for both of them, I would get a total area of 100.48 centimeters squared. Okay? And so if I compare the two, well, this is still double this. In fact, if I took 296 centimeters squared and I subtracted the 148 hundredths centimeters squared, I would get exactly 148 centimeters squared. Okay? So, 1 8 centimeter pipe can deliver more water, or whatever I just tried to write there. Okay. Then I would explain my reasoning a couple of different ways. First, I calculated the area of all of the pipes. I added up the two 4 centimeter pipes, and it was only half as much as the 1 8 centimeter pipe. I could also explain that when I found a radius ratio of 1 to 2, the area ratio ended up being 1 to 4. And that was true here. If I took 50 and 24 hundredths centimeters squared and multiplied it by 4, I would get 296 hundredths centimeters squared. So the radius ratio is 1 to 2, and so these radiuses add up to one of these. But the area ratio is 1 to 4, and so I would need 4 of these pipes, the 4 centimeter pipes, to equal the same area as the 8 centimeter pipe. So whenever the radius is doubled, I would almost consider writing this down. Whenever the radius is doubled, the area is quadrupled. Okay? And so based on that, they should use the 8 centimeter radius pipe.